Welcome back, students. Today we're going to look at what are called random variables and density functions. So to start us off, you can read through this. You can play this game if you'd like to, but we're going to think about this introductory activity. And it says, you want to operate a game at the school carnival for your school club. The game involves a board with the numbers 1 through 6 displayed. A participant places $1 on any of the numbers, rolls 2 dice, and wins $1 for each time the chosen number appears. They keep their dollar and get an additional $1 or $2. There are a few club members that feel that the organization would lose money on this game. Play the game and analyze it. All right, so if you want to, you can take the time and recreate the board and get out a couple of dice, or get on your computer and you can get dice off of the computer website. And you can play this game and see if you think that overall you're winning money or if overall you think you're losing money. But what this is an example of what's called a zero-sum game. The reason why it's called a zero-sum game is because if you're the participant and then you have the game itself, whatever money you lose, the game wins. So that means that if you were to add what you lose and what the game wins together, it's going to add to 0. So hence zero-sum game. All right. So in the past, I've played this with my previous Finite classes, and these are some totals that we came up with. We played the game 527 times one year. Not one person individually, but overall as a class. We have come up with 527 games that have been played, and 318 of those cases, the person that was playing lost $1. That meant that they put $1 on a number, and neither of their dice was that number that they chose. All right, and that is approximately 0.6034. For winning, the case that they won $1, which meant that they put their dollar on a number, one of their die showed that number, the other one didn't. So that's the case where they win $1. That happened 190 times out of the 527 times that this game was played, which is the decimal of 0.3605. And that would mean 19 of those games out of 527 is the case of when $2 was won, and that is approximately 0.0361. So this was the experimental probability. So for this game that was played 527 times, this is the experimental probability, which is leaning towards the fact that the participant, the player, is going to lose money more often than they win money. All right, now, this doesn't represent all of their totals exactly. This lose $1, yes, in the eyes of the person playing, this shows that that person lost $318 in this scenario. But at the same time, if they played all 527 games, then they would have won $190. And in this case, they would have won $2, and this happened 19 times, so they would have won $38. All right, so adding this all up, this would have been a minus 318 for the player, plus 190 for the player, plus 38 for the player, which would give us a grand total of negative 90. So what this means is that the player lost $90, but the game would have won $90. So overall, again, this is just experimental. This was based on an experiment that I did with a previous class. Overall, this game would have been a good game because it would have brought in $90. All right, so eventually it is my hope that we are going to do something like that, where you come up with a zero-sum game and come up with a carnival activity and analyze your own individual game. Today, what we're going to do is start the analysis of some of these scenarios. All right, so eventually we're going to be calculating this expected value of the event, but before we get there, we're going to discuss a few other items first. Expected value will be in our next lesson. So a random variable is a function that assigns a real number to each outcome of an experiment. All right, so in our intro activity, if we would have placed our dollar on the 4, the random variable would have been representing how many 4s were rolled. So we could have rolled 0 4s, we could have rolled 1 4, or we could have rolled 2 4s. So 0, 1, and 2, okay, those would have been our random variables. Those would have been our numbers that our random variable could have been equal to. And then if we put those random variables together with their probability and make a chart, that is called the probability density function. Sometimes it's called the probability distribution. All right, so here I have a table and it's getting started to represent the intro activity that we have up above. But X right here represents the random variable. Usually you'll see that as a capital X. Sometimes you'll have a lowercase x. But when we use random variables, we usually use a capital letter to represent that random variable. So our random variable, again, can represent that you rolled that number that you chose 0 times. You could have rolled it 1 time, or you could have rolled it 2 times. Now what we need to do is come up with the probability of this. All right, so this is going to be where you just need to take all of everything that you've learned so far about probability and you need to think, okay, how am I going to calculate this probability? Right. One thing that we should note here is one of these scenarios is going to happen. All right, so if we take all of these 3 probabilities, whatever we get in the end, these 3 probabilities should add up to 1. Okay, that was the case that we have up here in our experimental probability. Okay, but now here in our theoretical probability, that should be the same case as well because something's going to happen. All right, so guaranteed that we're going to have the sum be equal to 1. All right, so a lot of these, not all of them, a lot of these are going to go back to binomial distribution because you can usually think of these in a case of, did I have a success? Did I have a failure? Did I do it this amount of times? Can this experiment be repeated, and so on? So this is a case of what we did last class, which is your binomial distribution. All right, so it doesn't matter the order that those were rolled. So we're going to use a combination. We are rolling 2 dice, and in this case, we're saying that we don't have any successes. All right, so this is how many times we repeat that trial, and this is how many successes we have in that experiment, in that trials. And then we multiply that by the probability of a success. Okay, so think of a number that you chose. Okay, there's 1 number on that dice out of 6 numbers. So the probability of the success would be 1 out of 6. You raise that to how many successes there are, times the probability of a failure, which would be the complement, which would be 5 out of 6, and then raised to how many of those failures we have. So this is saying we don't match either of our dice, so this would be 5 6 to the 2nd power. Feel free to use a calculator, but that would give us 25 out of 36, which is approximately equal to 0.6944. Pretty close, actually, to what we had in our experimental probability. Anyway, continuing on with this idea, in the next case, we would have 1 success, and that would mean 1 failure. So this would be 2c1 times 1/6 to the 1st power times 5/6 also to the 1st power. And this is going to give us 5 out of 18, or let's keep it in terms of 36. This would give us 10 out of 36, which is approximately 0.2778. Then our last case is if we roll both of those dice to be the same number that we chose. So that would be 2c2 times 1/6 to the 2nd power times 5/6 to the 0 power. All right, and that is going to give us 1 out of 36, which is approximately equal to 0.0278. All right, so let's double check. 25 out of 36 plus 10 out of 36 plus 1 out of 36. That is going to give us a grand total of a denominator of 36. And 25 plus 10 is 35, plus 1 more is 36 out of 36. That's a really good indicator that our probability density function is correct. All right, and like I had already pointed out before, our theoretical probability compared to our experimental probability was pretty close when it came to our, if we matched it 0 times, that would have meant we lost $1. But then the 1 and the 2, okay, if we matched it 1 time versus if we matched it 2 times, that's where we were off a little bit. But again, experimental, theoretical, they don't always match. Okay, theoretical is in theory that would happen, and experimental is what you actually get when you run the experiment so many times. All right, a second example. It says find the probability density function for the number of heads shown when 2 coins are tossed. All right, so find the probability density function for the number of heads shown when 2 coins are tossed. So first thing that we need to do is define our random variable. All right, so density function for the number of heads. So that means that we're going to go ahead and use a random variable and let that represent the number of heads. All right, so what are the possible values for the number of heads? Well, we are going to flip 2 coins. All right, so if we have 2 coins, the first coin could show heads or it could show tails. Okay, and then we're going to flip again, and we could get heads or we could get tails. We could get heads or we could get tails. All right, so what we could have in this case, if we go tails, tails, that means that we have 0 heads. We could go tail heads, which means that we have 1 head. We could go heads, tails, which means that we have 1 head. Or we have heads, heads, which means that there are 2 heads. So once again, our possible values for our random variable are 0, 1, or 2. So making our probability density function, the top row, usually represents your random variable. And again, we have 0 as a possibility, we have 1 as a possibility, and we have 2 as a possibility. And then the second row of this table is representing the probability of getting those assigned values for our random variable. All right, so once again, this is a case of considered success or failure. It's a repeated number of trials, and so this calls for our probability distribution, or our binomial distribution, our binomial or Bernoulli trials formula. So order doesn't matter, but there are 2 times that we're going to flip this coin. And in this case, it's saying that we have 0 heads, and we defined having heads as a success. All right, so this is going to be 2C0, and then times the probability of getting heads is 1/2, so that would be raised to the 0 power, times the probability of getting tails, which would also be 1/2, and that would be raised to the 2nd power. All right, so multiplying all of this out, this is going to give us 1/4. All right, so the next case, we're going to have those 2 coin flips, but this time we're getting 1 head. So that'd be times the probability of getting heads to the 1st power times the probability of getting tails to the 1st power. And this is going to give us 1/2. Okay, and then the last case would be 2C2 times 1/2 to the 2nd power times 1/2 to the 0 power, which is the same thing as what we had before. Just the order has been switched around. So that's also going to simplify to 1/4. So 1/4 plus 1/4 plus 1/2, yes, that does add up to 1. So that's a good indicator that we have our probability density function correct. Example 3 says, find the probability density function for the following scenario. A team of students working on a project consists of 3 juniors and 2 seniors. 2 students are selected at random, and a random variable x is defined to be the number of juniors selected. All right, so define the random variable. Well, that was already defined there for us, is the number of juniors that will be selected. What are the possible values of the random variable? All right, well, if we are selecting 2 students, we could have well, you know what? We've been working with a lot of tree diagrams lately, so let's make a little tree diagram off to the side. All right, so we're picking 2 students. So on the first student, either a junior or a senior could be chosen. And if the junior was chosen first, then on the second student, it could either be a junior or a senior. Had a senior been chosen first, the second could have either been a junior or a senior. All right, so here are our possibilities. Let's actually make this easier on ourselves, and let's also use this tree diagram to help us with our probabilities. All right, so there are 5 total students to pick from for this first student. There are 3 juniors, so the probability of picking a junior on the first student would be 3/5, and for a senior it would be 2/5. On the second pick, one of the students has already been decided, so there are only 4 total students remaining. Had there been 3 juniors, but one of them has already been chosen, then that means that we have 2 out of 4, which would reduce down to 1 out of 2. And then that would mean that junior and senior, that would also be 1/2 because of complement rules. Also thinking of, had there been 2 seniors, none of the seniors were selected so far, there would still be 2 out of the 4 people left. All right, now think of the scenario if a senior is taken first. Okay, that means that on the second student, there are 3 juniors still remaining out of the 4 people. And had a senior been chosen first, there are 4 people, but 1 senior is already gone, which means that there's only 1 senior that remains. All right, so now let's get these and probabilities. So what's the probability of picking a junior and a junior? Well, that'd be 3/5 times 1/2, which would give us 3 out of 10. Junior followed by a senior would be 3 out of 10. A senior followed by choosing a junior. Simplify the 2 over 4, which would make it 1 over 2 times 3 over 5, which would also give us 3 out of 10. And then 2/5 times 1/4, again simplifying 2 over 4 to 1 over 2, that would give us, what would give us? 1 out of 10. And double checking 3/10 plus 3/10 plus 3/10 is 9/10 plus 1/10, that gives us 1. So this is a really good indicator that we've come up with a correct tree diagram to represent our scenario. All right, so again, the whole reason why I went to that tree diagram is because I'm trying to come up with what are the possible values of having a junior be selected. All right, so X represents our random variable. And in this case, we could do senior followed by a senior. We could do senior junior. We could do junior senior or junior junior. So in this case, we would have junior junior. So that means that there would be 2 juniors. In this case, we'd have junior senior. So that'd be 1 junior. Senior junior, that'd be another case of 1 junior. And then senior senior would be a case of 0 juniors. I promise you that your probability, or for your random variables, that they are not always 0, 1, and 2. But in our cases so far, those have only been our random variables that we have used. Okay, makes sense too, because I try to give you some smaller values to work with. All right, so now probabilities of these. Okay, we already have those over here. So the probability of getting 0 juniors would be this scenario, which was 1 out of 10. The probability of getting 1 junior, we have to do a little addition here because it could be a junior followed by a senior or a senior followed by a junior. Either way, it's 3/10. So 3/10 plus 3/10 would give us 6 out of 10. All right, and so not process of elimination, but using the complement rule, 1/10, 6/10, that adds up to 7/10. That means that this has to be 3/10, and we also have that up here. A junior followed by a junior, that probability was 3 out of 10. All right, so all of this together is the probability density function. All right, last scenario, it says find the probability density function if we have a box that contains 5 balls, 1 is blue and 4 are red. An experiment consists of selecting balls at random, one after another, without replacement, and noting the color of each ball selected. The experiment ends when a blue ball is selected or after a total of 3 balls have been selected. A random variable X is defined as the total number of balls selected when the experiment ends. All right, so they've already defined our random variable for us is how many balls it's going to take for us to end this experiment. So what I'm going to do first is, like I have been doing, is make a tree diagram of the scenario. Okay, that usually just helps us to visualize everything that is going on. So that's going to really help us with question number 2 and then question number 3, which is making the probability density function and just putting it all together. All right, so I should have enough room here. All right, so on the first draw, Okay, so put yourself into this box. If you want to get a box and actually make this scenario, make it. Okay, but you could either draw what were they? Blue or red. All right, so B stands for blue, R stands for red. All right, it said that there are 5 balls. All right, so our denominator is going to be 5. And our numerator, there's 1 blue ball, and there are 4 red balls. So this is going to be 1 out of 5 and 4 out of 5. Okay. Before I just start going off and then saying blue, red, blue, red, blue, red, let's think about this a little bit. Okay. It says the experiment ends when a blue ball is selected or after a total of 3 balls has been selected. All right. So if on the first draw we have a blue ball, it says that is when an experiment ends. All right. So I'm going to go ahead and, put a star right here saying, hey, this would be, if this happens, this is the end of the experiment. Okay, but if this happens, the experiment keeps going. All right, so on the second draw, we could either get a blue ball or we could get a red ball. Okay, the first draw was red, okay, which means there had been 5 balls, but it says without replacement. So that means that there are now 4 balls remaining. There's still 1 blue ball in there. The first ball drawn was red, so 4 minus 1 means that there are only 3 red balls that remain, and these add up to 1, so that's good. Okay, once again, I'm going to put a star by this blue because selecting a blue ball ends the experiment, or having a total of 3 balls been selected ends the experiment. All right, but this would only be 2 balls selected, so that means that this scenario would have to keep going. So we could either draw out a blue ball or a red ball. There are now just 3 balls that remain in this box. 1 of them would be blue, and 2 of them would be red. All right, and so once again, blue being drawn is going to end the experiment. But again, red, 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 this is 3 balls in total, so this is also going to end the experiment. All right, so I know how my experiment's going to terminate. Okay, and I've started working with my probabilities. I just need to get my probabilities for all of these possible paths. All right, so this one's easy. This one's just going to be 1/5. All right, so what's the probability of ending the experiment by getting red followed by blue? Well, that's 4/5 times 1/4, which is also going to give me 1/5. All right, what's the probability of ending the experiment by going red, red, then blue? Well, I need to multiply 4/5 times 3/4 times 1/3, and then simplify all of that. And after I simplify all of that, it also simplifies to 1/5. So then 4/5 times 3/4 times 2/3, multiplying all those together, that simplifies to 2/5. And then double check 1/5 plus 1/5 plus 1/5 plus 2/5. Maybe I should circle those so I don't get confused with some of my others. Okay, all of those add up to 1. All right, so that's a good indicator that my tree is correct. All right, so the point of this, I got all my probabilities, but I also need to figure out what are my possible values of my random variable. All right, so the random variable is defined as the number of balls selected when the experiment ends. All right, so the experiment ended here. There was 1 ball that was selected. It was blue. I don't care about the fact that it was blue. What I care about is the total number of balls. All right, so my random variable x is representing how many, and 1 is going to be the least amount of balls that could be drawn in order to end the experiment. All right, here's another scenario, and that was red followed by blue, which is 2 total. And then here's another one, which is red, red, blue, which is 3 total. But this is also red, 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 which is 3 total, so 3. All right, so in this case, our possible values of the random variable are 1, 2, and 3. So finally something a little bit different than the standard 0, 1, and 2 that we've seen so far. All right, so now to finish this, we're almost done. The probability of these, we just need to grab those from up here. So the probability of having this experiment with just 1 ball taken is 1 out of 5, 1/5. With 2 balls, that was also 1/5. And with 3 balls, it's these 2 together, so 1/5 plus 2/5, which would make it 3/5. There we go. All right, so Not much that we are doing today. Random variables usually go with expected values, and we have split those up into 2 separate days. So this is just really figuring out how can I assign numbers that represent my scenarios, and then how can I come up with the probabilities of those, put it all together, and that is called your probability density function.